Hello and welcome. I hope you are having a great day. In this video, we are going to understand about hypothesis testing. It's a very important concept with respect to machine learning because once the models are ready, we need to evaluate them, how the model is performing. Is it better than the baseline model or the previous model that we created? Or in case we have to compare two models, so model comparison. Also when we are doing A-B testing. So this concept is used in all these things. Okay, let's understand. So let's set up the agenda first. I hope the screen is visible. So we'll understand, okay, what is hypothesis testing. I told you why is it required, why do we need to study hypothesis testing. Okay, then what is it, we'll understand. Then we'll see a 6-step framework to perform any hypothesis testing using any test statistic. Then we understand some more details around that, like what is a left-tailed or right-tailed test or one-sided or two-sided test. Okay, it's called tailed or sided depending on, because the curves are like this, so you have two tails on both the sides, right? So we'll see what kind of test is required for which kind of scenario. We'll understand that. Then we'll discuss about critical value. What is the critical value? When we are discussing about that, we'll discuss about p-value also. P-value we'll discuss during the hypothesis testing framework also, but again it will come here. What is the p-value? And then we'll understand what is power of a test, and then finally we'll understand effect size. Okay, so this is the agenda. Let's start one by one. First thing, so first of all, hypothesis testing. What is, so there are two words in this. Okay, so let me write it down. So first of all, what do you mean by hypothesis? Okay, so we'll do a testing, that's later, but what's the literal meaning of hypothesis? Hypothesis in general is an idea that is suggested as a possible explanation of something, but that has not been validated yet. Okay, and that's what we do when we test it. So you propose a hypothesis about an idea that something is like this because of such and such reason, but that idea, whatever suggestions you have made, has not been validated as true or false. And on basis of the data, we'll finally test whether your hypothesis or the suggestion or the claim that what you are making, whether it's right or wrong, true or false. Okay, I hope that is clear now. Hypothesis is a suggestion or a claim that something works in a certain way, and then later this has not been proved yet whether it's right or wrong, and the testing part proves that whether it's right or wrong, true or false. So that's the two parts, hypothesis and testing. So hypothesis means a claim that something, or a suggestion, a proposal, something as a, that is a possible explanation of something, possible explanation of something, but has not been validated, or has not been validated or found as true or false. So this is the hypothesis part. And testing we know. So since it has not been tested yet, so we'll test the claim. Okay, whether model A is better or model B is better. So I say model A is better. Okay, but this is just a hypothesis, and then we'll collect data for both the models, and finally based on the basis of data, we'll finally find out whether the claim that I'm making, model A is better than model B, whether that claim holds or not. So that's hypothesis testing in a broad way. Where it is used, generally it has been there for a long time. It's being used in machine learning also. This concept is very old in statistics. So they're generally companies, okay, they test, say for example, their marketing campaigns on very small sample of representative data, and based on that they will take then larger initiative or make a larger investment if the marketing works fine. So that is the basis. This on the basis of whatever data they get, whether whatever we're thinking that this marketing campaign will work or not, based on the input they get from the customers. Okay, that's, they take as it as a representative sample for the complete group or complete population, and based on that they take the larger initiative or a major business decision. So this is the practical use case apart from machine learning also. It has been there in statistics. Okay, And it also, and instead of analyzing the complete population, that's what we have seen in statistics, we cannot analyze the complete population or the group data, right? We cannot, if I have to find average height of people in a city, we cannot find or capture the height of each and every individual in the city. So we take a representative sample, and then we do take a average of that, and we say that this is the representative of the population mean. And that's what we do in hypothesis testing also, all over statistics. We take a representative sample because practically it's impossible to collect the data for the complete population. Okay, and on that we do the testing. So whatever sample data we have collected, and that is a representative sample. So let's formulate what is it. So this is a this comes from statistical okay, this is a statistical inference framework. We want to infer something from the data. So what is hypothesis testing? So this is a statistical, so this is some theoretical part, statistical inference. We want to infer something from the data, whether some claim is right or wrong. Inference framework, that's what it is. Okay, used to make decisions about a population. So it is used to make decisions about a population parameter. Okay, so the population parameters can be we can make decision about the mean. Okay, it can be variance. It can also be the distribution, what kind of distribution the population has, the underlying distribution of the data, and so on. Other things also, correlation between two variables. So this can be done on basis of the sample data. We can make conclusions about the population parameters. This can be population parameters, and we make decisions about these parameters based on sample data. On the sample data, we perform the hypothesis testing, and we make claims or inferences or give possible explanations about whether the mean of whatever, say for example, if I say the height of average height of a city is like 5 feet 6 inches in India, and this is my population, I claim that this is the known population, and then I collect a sample, and then I match this, try to compare the two populations, whether they are same or whether it's close to the mean or not. So that is with respect to a known population mean. And then sometimes we can compare the average of two groups, average salary of one company against average salary of another company, and we can compare the two means. So mean can be a representative. Similarly, we can compare like two distributions. So I have two set of data, whether they come from the same distribution or a different distribution. Underlying distribution is it Gaussian for both, or is it Bernoulli for both? So that kind of decisions also we can make. Mostly we talk about Gaussian only, whether both of them come from normal distribution or not. And there are different set of tests for that. Okay, so I hope this is clear. What is hypothesis testing and what does it measure? Okay, so this gives you a formal framework. So this is the formal method to do all this. Instead of all these, there are a lot of tests, and there are a lot of distributions. So how do we make use? There should be one uniform framework, so which will allow me to use, plug and play any test statistic, any test, any distribution, and make some conclusion out of the data that I have. So that's what it is. It gives me a formal method. Okay, it gives me a formal method. It's a formal method. We formalize everything. Formal method to evaluate claims or competing claims. Okay, to evaluate two claims competing, like one is against each other. One person says that A is better or B is better. Okay, so there are some terminologies which will get used to whenever you talk about hypothesis testing, and those will form the base of it. So you should know these terms. So as soon as you talk about hypothesis testing, so we have first thing that comes is null hypothesis. Okay, these are the terms that you should know. Null hypothesis. This is represented as H0, 0 as a subscript. So what is null hypothesis? Null hypothesis is status quo. Nothing has changed. Whatever was there, it is as it is. There is no difference between the two samples. That is always the null hypothesis. That means that there is no change. Status quo, no change, no difference between two means. So generally that is the null hypothesis, that nothing has changed. Both are same, everything is same. If I'm comparing two things, it is same. Okay, nothing has changed or there is no difference. That's what is my null hypothesis. Means nothing has happened. Even if I'm like if I'm doing drug trials on using two medicines on two set of patients, so I say that both the medicines are same, nothing is different, both are same, everything is same. So that's what is broadly null hypothesis, that everything is same, no effect has happened there, nothing. Whatever tests are conducted, it didn't have any effect, anything that is negative, no effect. That shows that there has been no change, no effect, no difference. That is your null hypothesis. So almost always it contains a statement like equality. Nothing has changed means what was earlier, even now it is same. Or when I compare two groups, so both the groups are having same parameters that I'm measuring. Okay, whether it's a mean or a variance or distribution, I assume that both are same. So for example, if I'm testing mean of two samples, okay, average height of two samples, then I can say mostly it is an equality, both are equal. Okay, so this is a statement of equality. Almost always that will be the case, unless until you formulate it in a different way. So I will say that mean of the first group is equal to mean of the second group. Mean height of the first group is same as the mean height of the second group. Two samples I have collected from two different samples. Okay, representative. That's your null hypothesis. I hope null hypothesis is clear. Then we have the alternate. So one is null, nothing has changed, and there's a alternate hypothesis which is called as HA or H1. Okay, so instead of 0 we do 1, or we say HA. A is for alternate, so that's the subscript. This is how we note it. So this says that there is, so just the opposite of it, there was some effect, there was some change, there was some difference, and whichever statement captures this means alternate hypothesis says that the opposite of null hypothesis, that no, there was some change, there was some difference, like mean 1 is less than mean 2, or mean 1 is greater than mean 2, or mean 1 is not equal to mean 2. It can be both of the things. So it says that there is some difference. Okay, so whatever, it's just the opposite of null hypothesis, that this is a statement which represents some change. These both are statements, claims. Okay, some change, difference, and all things that is opposite. Okay, there is some change or difference, and this must be okay, and this will be true automatically. So either of these will be true. Generally all the testing is done on null hypothesis only, everything is done on null hypothesis, and the basis is like whether we accept or reject. If we accept the null hypothesis means nothing has changed, and if we reject the null hypothesis means the alternate hypothesis is true, means there is some change or there is some difference. So this is accepted, must be true. This will be true only if the null hypothesis is false, and all the tests are done on this only. Simple, because it is easier to validate or test only one condition than simultaneously testing both two conditions. So we just focus on the null hypothesis, do everything on this. If it is true, no problem, nothing has changed. If it is false, then we automatically fall back and conclude that my alternate hypothesis is true. Okay, so what does it say? This must be true if null hypothesis H0 is rejected or it is false. Okay, and then generally it is not equal to or less than. So for example, what will be, as I mentioned here, statement of equality, here it is not equal, that something has changed. So it will be it will be like, for example, my mean 1 is not equal to mean 2, is not equal to mean 2, or mean 1 is less than mean 2. Such kind of statements, there is some difference. Okay, I hope these terms are clear. Slowly we'll introduce more terms, and as and when they come, I'll explain you what that is. This is null hypothesis, this is alternate hypothesis, and let's move to the framework. Okay, so before that, let me discuss about what kind of, so you get acquainted what kind of tests we do. Okay, so there are some, I won't cover all the tests, but I'll give you some most common tests that we perform. So I'll just write types of hypothesis testing. Okay, so I'll write types of hypothesis testing that are most commonly used. Generally we compare. Okay, we'll start with the first one. The first type is when we compare means. Okay, We do test of means, whether the means of two sample is same or not. It is called test of means. Mean is the average. Okay, test of means. So either it can be a one sample t-test, one sample mean test. Okay, that it can be like one sample mean test, or a two sample mean test, or it will be paired. I'll tell you what all of them mean. One sample means I have one set of sample, okay, and generally we compare it with against the known population mean. So if it is around the mean, right? So I have a sample and I compute a mean of that, and I have a known population mean. So I compare the sample mean to the known population mean. So that's where it is one sample. I have only one set of sample. That I have one set of sample, say average height of people from one standard 10th class, and I say that the average height is this much. I know that is the population, and whether the sample that I have collected is it representing the same value or not. So that will be why one sample mean test. Okay, so that is compare sample mean to population mean. New. Okay, so that is one sample. Two samples means when we have two groups and we want to compare two groups using their mean, then we use two sample mean test. So that is like x1 bar, compare x1 bar if there are two groups to x2 bar. Both the sample means will be compared. Okay, and the paired is generally before and after of the same sample. If something has happened, and then what is the mean after that and before that. So when before and after change we have to measure, then we go for paired test. This is not so common. I won't discuss further also, but I have just mentioned it so that you know that this exists. And whatever I'm discussing, this is not exhaustive. There are only more kinds of tests that are, but these are most common, so that you should know. When you hear of it, you should know that you have heard of it. Okay. So paired test is like compare means when data is paired. For example, before versus after test. Okay, so this is before versus after of the same. Before versus after mean. Okay, so mostly even when I discuss about z test and t test further, so I will only focus on one and two sample tests. I won't discuss the paired test, but you should know this is there. So the other test of means, so all the central tendencies or everything whatever we have discussed in the last video, right? So the central tendencies or the variance and the distribution, everything can be compared. So the next one is like we can test of medians. So if we have mean, we can test the medians also. We can test the medians similarly. So there are a lot of tests. So within this test of sample mean, most popular here are, we take t test, z test. Okay, I'll discuss about that in detail in separate videos, but t test and z test is there. Then we have test of medians. This is simple. I won't. You should know that there are a lot of there are moods median test. Then there's Wilcoxon also. Wilcoxon signed rank test. So just know this. There's sign test also. Just know about this. So most common is moods median test. Okay, but I won't discuss about this. Just know that. Then we have test of variances. When we compare variance, then we have test of variances. Variance, you know, right? So we have generally chi-square test. This we will discuss at length in a separate video. Chi-square test for single variance. Chi-square test, there are a lot of chi-square tests. We'll discuss all of them. Or at least we'll discuss about two major. Okay, for a single variance. Then we have F test. F test. This is also common distribution. F test to compare two variances. Then we have tests of distribution or goodness of fit. Then we have test of distribution, or commonly we said goodness of fit, whether This is more common nomenclature, goodness of fit. So we'll discuss about chi-square goodness of fit test. Goodness of fit generally that is written as GOF. Okay, goodness of fit test, and then we have Kolmogorov Smirnov test, KS test. Then we have Anderson-Darling test. Then we have Shapiro-Wilk test. There are a lot of them. These are common goodness of fit. Then you have test of correlation. Correlation, you know, right? We have done this in the last video also. Check that video. I'll put the link in the description. Correlation is like the Pearson correlation coefficient. Pearson correlation. That is there. And then also there's a chi-square test of independence. Even we can use that. I'll discuss about this also in other videos. Chi-square test of independence. Okay, so these are the broad, more important ones which we'll discuss, and then there are regression related tests, etc. So I'll not go into them, but broadly these are the ones which are most frequently used, and there are more depending upon your use case. You can just go and search them online and you will get it. Okay, test of means, test of medians, test of variance, test of distribution, goodness of fit, and then test of correlation. Okay, there is Spearman's rank correlation coefficient also here. So these are used. Now let's move to the framework. That's the next topic. So what is the framework? The 6-step framework for hypothesis testing. So let's write the framework for HT. I'll write hypothesis testing in short like that. So there are 6 steps using which we can break down, or using these 6 steps we can do any hypothesis testing. Okay, let's understand them one by one. So I'll give you the framework first, and then we'll run through one example so that you understand each step clearly. What is the meaning of each step when I'm saying? And in later videos, when we do more of like when I do students T test, Z test, chi-square test. Okay, so you go and follow. I'll put the link of those videos also in the description. If you go and follow them, you will get more and more better idea of what does each and every step mean. You need not do it in exact way, but if you have these concepts clear in mind, then automatically you can do any hypothesis testing. It's just to break it down and so that you understand these 6 steps. Okay, to start with, and later on as you get comfortable, you can just put all of them together in any order. So let's proceed with the framework for hypothesis testing. Okay, so first and foremost, for any hypothesis testing, what we do, we state the null and alternate hypothesis. So first step is state the null and alternate hypothesis. State null and alternate hypothesis. Okay, first of all, state clearly what is the null hypothesis, what is the alternate hypothesis. Okay, then step number 2. Step number 2 is select a relevant statistical test for the test statistic. So depending upon your task, you will choose what kind of test statistic are you going to implement here. For example, if your sample is less than 30, then you can go for student's T test or T test simply. If you have greater than or equal to 30 samples and you know the population standard deviation, then you can go for Z test. Okay, so the second test is select a relevant statistical test that is relevant for your use case. Select a relevant statistical test. There are a lot of statistical tests. Out of them, what makes sense in your case? F test. Then there is whatever you have mentioned there. All this goodness of it. Chi-square test, F test, etc., etc. Okay, just think. The third step is derive the distribution of the test statistic. Okay, under null hypothesis. So assuming that the null hypothesis is true, we derive the test statistic value. So derive the distribution. Derive the distribution of test statistic. We call it test statistic under null hypothesis, or assuming that null hypothesis is true. For example, for normal distribution, okay, normal distribution which is Z test, we will with the Z test with known mu and sigma, So that will be the distribution of that. If you're using for the for a sample which is a normally distributed sample, then we can use the z-test statistic, and with a known mu and sigma, I will get the distribution of it. What will be the distribution will be like this. Okay, so that's the third step. Then the fourth step is select a significance level. Okay, so I'll talk about this. Select a significance level. This term also, what is the maximum acceptable false positive rate. Max acceptable false positive rate. Generally, denoted by alpha, is equal to, generally it's 5%, also 1%, and for medical it is even less, 0.1%. I'll discuss about that. Medical test it is even less. So generally 5% is the norm. That's the alpha or significance level. If it is beyond that, then I'll accept the null hypothesis, that I am willing to accept 5% false positive rate. If you don't understand false positive, I'll discuss about that also in this video only. Now compute the p-value. The fifth step is compute the p-value. I'll discuss about what is the p-value also. All the terms will be clear. Compute the p-value from observed whatever. Once you have the distribution, you have the distribution of the test statistic. From that, whatever is the value for under the null hypothesis, you will compute the p-value from observed value of test statistic. That is, generally we write it as t observed. T is for the test statistic, OBS is for the observed. So we'll compute the p-value, and then finally on the basis of this, decide to either accept or reject your null hypothesis. The 6 is accept or reject null hypothesis based on whatever is the significance level that you have seen, based on alpha. Alpha is your significance level. Alpha, p-value, these are important terms. These are your 6 steps. We'll come back and revisit it again one by one. Let's understand it using an example. Let's do. So let me state a question for you so that you understand better. So the question is that we have to do the hypothesis testing to compare the mean recovery time of 2 drugs or 2 medicines. We have to say I have one medicine which treats some condition. So I have to compare which drug is better. So I have to compare the recovery time, and we'll use the mean of the recovery time as our metric to compare the 2 set of medicines. And each medicine is tested on some set of patients, some number of patients, and there are 2 groups, and now we have to compare these 2. So we don't know which is better. So now, based on the data that we have, we will see that how to formulate. So today we'll not solve the problem exactly, but this is to explain you the framework. And when we go into exact tests, t-test, z-test, or chi-square test, then you will solve exact problems. But this will be too much for you. So today I'll just explain you the concept using broadly, or meant to explain the framework to you. So the question is, do the hypothesis testing. Do the hypothesis testing, HT, to compare recovery time, recovery time of 2 medicines. So you have to do this, medicines. There's a medicine 1, medicine 2, and we have some data. So for example, the data is in the format that you have patient ID, then whether medicine 1 or medicine 2 was given, and then there was recovery time in days. For example, patient ID 1, medicine 1 was given, and the recovery time was like 7 days. 2, medicine 2 was given, recovery time was like 8 days. 3, and so on, like that. You have some sample. This is the data you have, this is the data you have. And based on this, now you have to tell which medicine recovery time is better. So that's the hypothesis testing you have to do. So we need some metric to compare these two medicine, two groups. So here we'll choose so out of this, first of all, we choose that we'll go with the mean to compare. If the mean recovery time of medicine 1 is less or mean recovery time of medicine 2 is less, whichever is less, that is better. That's what we can compare. So we'll choose mean as the metric. So we'll choose mean recovery time. Okay, and let's denote it by for the 2 mean recovery time as mean recovery time for medicine 1 and mean recovery time for medicine 2, like that, mm1, mm2. Okay, so this is the setup. We have to compare now which one. So depending upon what we have, so we will find out which is better, and depending upon the thing that we want to find out, that tests will vary. The alternate hypothesis will change, the hypothesis will change. Null hypothesis always remains the same, that both are same, nothing is changed, status quo, both the medicines are same, everything is equal. So that will be my null hypothesis. So there are two things that we can use here. So we can use t-test, as I mentioned earlier. So first thing is, what are the choice of tests we can use? So state the null and alternate hypothesis. Okay, so first of all, let me test. So null hypothesis, I will say that both medicines have the same recovery time. So my same recovery time means medicine M1 recovery time, mean recovery time of medicine 1 is equal to mean recovery time of medicine 2. This is my null hypothesis, that everything is same, nothing changes. And my alternate hypothesis is, this is my step 1. Now depending upon later on when we go for 1 and 2 tail test, right? So depending upon what is my alternate hypothesis, the type of test, the way we are measuring it will vary a little, because everything is a distribution. So we'll see which tail to look at. But let's go with the simple one first. So alternate hypothesis is that no, both are not same, and I'm claiming that my mean recovery time of medicine 1 is less than mean recovery time of medicine 2. That's what is my claim. It can also be the other way around, that it is not, or it can be like both are not equal, just this one. But for this, we'll go with this 2 for first. Let's easier to understand. Not equal to is even more complicated. Okay, so my null hypothesis is that both the medicines are same, nothing has changed, everything is equal. And my alternate hypothesis is that no, mean recovery time of medicine 1 is less than mean recovery time of medicine 2. Means medicine 1 is better. This is my alternate hypothesis. So we'll go and verify this. If it is valid, we'll accept it. Okay, if we find it, or else if we don't find this is true, then we reject it, and automatically this will become true. So this is my alternate hypothesis for this case. And what are the tests? So second, this is step 1. Step 2, select a relevant statistical test. Relevant statistical test. So what are the choices that we have? Step 2, relevant statistical tests. So I have two options here. For example, either I can use t-test, student's t-test, in case the number of samples is less than 30. Generally in medicines, we have because we cannot go and conduct medicine test on thousands and thousands of people, right? Even they do it, but generally when statistics came into play, the sample size was very small. Okay, when these tests were invented, student's t-test. So generally n less than 30 is what we can expect in medicinal trials. So n is less than 30 plus population standard deviation is not known. Population standard deviation, that is sigma, is unknown, because for such a small population we don't know anything. Or we can use the z test. These are the options 1 and 2. That n is greater than or equal to 30 means the sample is large and my sigma is known. Okay, so depending upon these, so I'll check. Okay, so when I look at the sample data, I will know which condition is it meeting. Say for our case, I'm going with the t-test and the number of samples is less than 30 and the standard deviation of the population is not known. So I'll go with the t-test. So I've chosen this. Okay, so I choose t-test, and this I'll continue throughout the example. Okay, so step 3 is, what is the step 3? Let's see. So derive a distribution of the test statistic under null hypothesis. So first of all, I should know what is the test statistic. Okay, so the test statistic would be, first of all, all these tests have a test statistic. So let's see what is the test statistic there. So for t-test, and here we are comparing two means, right? So it is a 2 sample mean t-test. Okay, that's what we are doing. We are comparing 2 samples, mean of one with another mean. So we are doing this. So what will be the test statistic for this? So let me see. So if I am not mistaken, we'll see this again in the test t distribution. But for now, let's see that this is my this is for same variance. And remember, same variance. Okay, let's not go into the details when I discuss Schwann distribution, then I'll say. But let's see, I'll give you the test observation. This is my test statistic. Okay, so my mean 1 and mean 2 comparison, it compares to mean, and then we standardize it so that the test becomes standard. Standardize it with the divide it with its means, s1 square by n1 plus s2 square by n2. Let me write it for you. What is this? So mm1 is the mean, sample mean of m1 and n2, sample mean recovery time, whatever was the recovery time. S is the sample standard deviation, and n1 is equal to sample size. Okay, so this is how you do a 2 sample mean test. So you have 2 means, you just do a subtraction, you can take the subtraction of them, and then you can just standardize it by dividing them with the, this is a standardized standard deviation. Okay, so we have standardized it. So this is a s1 square is the variance, right? A square root of that is standard deviation. So if you divide, both are same units. So for example, if this is in days, mean recovery time, so even this will be in days, this will be day square, and finally this will be in days, so days by days, this will become unitless. Okay, so this is your test statistic. Now this is clear. So if the 2 means are very close, what happens if the 2 means are very close? If they are very, very close, this is saying null hypothesis, that if both are very close, my t observed will become 0. It will be close to 0. If both are very close, and then this will be close to 0. For example, if this is the kind of distribution, assume even t distribution is symmetrical, but its tail is a bit different. Okay, and say this is your mean. Okay, if both the means are different, this is your distribution of the test, this t observed, this is the distribution of t, this test statistic, that is this distribution, this is the PDF of t test or t distribution, sorry. So it also has degree of freedom, etc. I'll not discuss that now, that is there in the other video. So it is the PDF of t distribution, and this is mu. So if both are very close, that is my null hypothesis, both are almost same, there is no difference between them, so it will automatically come near 0, right? And if both are not same and there is a vast difference, they will go away from 0. So for example, if mm1 is less than mm2 otherwise, so it will go this way or this way, it will go away from the mean. I hope that is clear. Okay, so keep this intuition in mind. We'll use it later when we understand how to accept or reject it, and when we understand p-value and critical value, etc. Okay, so this is your step 3, that I have now a test statistic with a known distribution. So I have the distribution for it. Derive the distribution of the test statistic. My test statistic for the t-test, 2 sample mean t-test is this. This is the test statistic. I have all the values. From the sample I can compute, right? I have the sample. From this I can, all these data, from this I can compute the mean for m1, for m2. I will have the standard deviation for both the values, for m1 and m2, and n1 and n2 is the sample size. I have all these values. I can calculate the t observed from this simply. Okay, and then I'll see, and I know that this is a t distribution. I can go and find out the t distribution for the given data, and from there I'll find out where is t observed on this. Whether both are equal, then this will be close to 0, or whether there is a lot of difference and they are close to the tail somewhere here. The t observed is coming here somewhere or here somewhere, depending upon the alternate hypothesis, whatever we have. So where it is lying on this, and depending upon that we'll do further analysis. I hope step 3 is clear. This is very important to understand. Now what is my step 4? Select a significance level. Max acceptable for false positive rate. Generally that is 5%. So let's select it as 5% only. So my step 4 is select some alpha, and I'll select alpha is equal to 5%. This is my significance level. Generally this is selected. 5% is my tolerance level. What is my step 5? Okay, what is step 5? Step 5 is compute the p-value from observed value of t statistics. What is p-value? Okay, understand this. So let me draw so whatever I've drawn this, let me draw it again. So say for example, this is the t distribution. Okay, this t distribution is also symmetric. This is the t distribution, and now I have to, you get the, say for example, if you get the t observed somewhere here, the value that I calculated, this is your t observed, this one t observed, you get it somewhere, this is your t observed. Okay, so what will be my p value? So my p value is equal to probability of seeing any value t which is greater than or equal to t observed. So this is a PDF. This is a PDF of t distribution. So what is the probability of seeing any value which is greater than or equal to t observed? If I want to find it from the PDF, the complete PDF is, this complete area is 1. Right? If I want to compute anything which is greater than mean, so I'll move here towards the right, the area under the curve. So that's what will give me. PDF area under the curve gives me the probability, right? In the PDF. So here, how will I find the probability of observing something greater than or equal to t observed? If I find the area under the curve which is here, right? If I find the area under the curve which is there, this area under the curve, that is the probability. This is my p-value, the probability value, the area under the curve which is greater than or equal to t observed. Okay, I hope this is clear. So let me shade it for you. So this is your p-value. Okay, the area under the curve. The area under the curve gives me the probability, right? So this is the probability of observing something greater than or equal to any t which is greater than or equal to t observed, this and beyond. I hope p-value is clear. Okay, and say for example, this area under the curve comes out to be, so either there are only two possibilities, either it can be less than 5% or greater than 5%, and also we have to find out whether this 5% step applies, right? 5% is the area under the curve, right? This 5%, this complete is 100%. Is the area equal to 1? PDF area is 1, right? So where will be the 5% line lie, so that the area beyond this is 5%? Say for example, in this case, let's point it. Say for example, this is that point, that is alpha, and this is t alpha, and this area is equal to 5%. The significance level. It says that at least 5% of the area under the curve should be at least 5%. The total is 100%. So this is your t alpha. Now think, my significance level is that at least 5% false positive I can accept. Okay, max, not at least, max 5% I can accept here. Okay, so what it says, that if it was here or it is greater than this, my significance level, okay, then I can accept my null hypothesis. Means, say for example, this is your mu. So understand, this is the difference between them. They should be very 0 0. It should be 0 ideally under the null hypothesis. But I'm saying even if it's not 0 till here, if it is here, okay, if it is till here, then I'll accept it. But if it goes beyond this, till here the complete area under the curve is 95%. This is the region. For example, let me color it with the different color. Let me color it with orange. This is the remaining area. So if it is in this region, this orange one, it should be ideally close to 0. Both the means should be same. That is my null hypothesis. But even if it is still here, so that my 95% of the area is covered and the remaining 5% is not covered. Okay, so this is my significance level, that okay, 95% of the area also it falls, no problem. Okay, and this 5%, if it is more than this, then I will accept it. So this will be our acceptance region. They call it acceptance region. So beyond this T alpha has got a name. Okay, this T alpha is called critical value. Critical value. So this is the test statistic beyond which my area would be equal to the significance level in this, that is 5%. And if my observed comes 5% or more, okay, 5% or more, this because this area is 5%. If you go this side, this will be greater than 5%, this area. So it will be beyond 5%. So it comes in the acceptance region, we accept it. But if you go beyond this, the T observed, if this moves this side, this will go less than 5%. So now this has become, so say for example, this is T observed is less than 5. Say for example, this is only 3%. My P value is only 3%. Okay. So this is less than your T alpha, less than the critical value. So I'm willing to accept something that is like till 95% if I'm getting. But if it goes beyond this, I'm not going to accept it. So if it is falling, my T observed is falling in this alpha or this region. My T observed is falling anywhere here. Okay, anywhere here. So I will accept it. But if it goes beyond this, the area under the curve will become less than 5%. So my P value will be less than alpha and I will reject the null hypothesis. Here this is 3%. And I wanted that at least 5% should be there. That's my significance level. At least this much should be there. Okay. So this blue region will be called, they have a name. This is called rejection region. Means if my T observed goes beyond T alpha, then I'll reject it. If it is less than T alpha, I'll accept it. And this T alpha, the area of the curve beyond which it is 5%, that is my critical value, and the P values beyond which my T observed, the area under the curve is there. I hope this is clear now. So here what is my P value? My P value is equal to 3%, which is less than T alpha, which is less than alpha, that is my significance level, alpha equal to 5% or significance level. We have computed this now. And these values generally we have charts as you have log tables, right? So we have tables. So we have z-score or t table for other chi-square test table. Also we have test tables like we have for log, for which value. We check that table and find out for each value because it's difficult to compute. So they are ready-made tables and from the table we'll see the value. What is the value that is there? And depending upon that we'll get the value. And if my T observed goes beyond that, in this case, then if it is greater than, because it is 0 is here, it is going greater than this, so I'll write it as 0 so that you don't get confused. This is 0. So the area under the curve becomes less and less, and now I cannot accept it. This has gone in the rejection region. So I will, in the step 6, what is my step 6? Accept or reject null hypothesis based on alpha. So here, as I have explained so much, my null hypothesis will be rejected. So I reject null hypothesis. If I reject null hypothesis means automatically I accept alternate hypothesis. That means that mm1 is less than mm2, whatever is the hypothesis. This is just for understanding. Okay, so I'm just showing that whether how to accept or reject. I hope these 6 steps are clear. Okay, so we discussed about critical value, beyond which the area under the curve will be equal to significance level, and if my t observed is towards the, in this case, towards the right of it, then automatically the area under the curve will be less than significance level, then I will reject it. If my t observed was here somewhere, for example, if my t observed was here, then the area under the curve will become greater than 5%. If it is here, say for example, this becomes 7% or maybe 10%, right? Then automatically this is greater than, my p value will become greater than alpha, right? This will become greater than alpha, p value. Then I accept the null hypothesis. So if my t observed was here, the area under the curve of this would be greater than alpha, and I will, because this is just the PDF's area, this will be my, because this checks the probability of t greater than equal to t observed. I hope this is clear. Shall we quickly revise it once more? Let's do it. So step 1. So what are we doing? We are comparing the mean recovery time of 2 medicines, and we have some data. Step 1, have the null and, so get your null and alternate hypothesis. We had the null hypothesis that mean recovery time for medicine 1 and medicine 2 both are same. Alternate hypothesis, no, that they are not same, less than or not equal to. Not interested in this. I'm not explaining that now. So I'll go into the details of this later, just after this. So this is the thing which we want to accept or reject. So we have this in place. Now we have to decide what kind of test are we going to use. What kind of test statistic will be there. Okay, what kind of test we are going to use, and depending upon that my test statistic will come. So we decide that we'll go with t-test because my sample size is less than 30. Then we found out what is the test statistic. We saw the t observed, and then we found the test statistic, and we got the distribution. The distribution will be known for the test statistic, and we got that, and we calculated the value for t observed. In the next step, we decided what will be my significance level. That is 5% is standard. We say kept it 5%. That's my significance level. In the next step, we calculated the p-value. P-value is the probability of area, probability of seeing any test statistic that is greater than or equal to t observed. So here, this is my t observed, and this is the probability of seeing. So this is a PDF of some test distribution, some t distribution. It can be t distribution, normal distribution, whatever test, chi-square distribution, depending upon the test we will have. Here it is t distribution. Okay. So the t observed area, with the greater p-value is the area under the curve beyond t observation, t observed. Okay, that is for t which is greater than or equal to t observed. What is the probability? So this is the area under the curve. Here we'll get this value from the table. Okay, what is the value? We can get the corresponding value. Similarly, for this significance level, we get a value that what will be the area under the curve for this t alpha. So we'll have the 5% number. We'll get this t alpha, t value, t alpha. We'll get the t observed from here. We get the t alpha from here. So we can easily compare where my t alpha is. In this case, if we want to compare p values, we can just compare if t alpha. I'll write it in different terms. If t alpha is greater than t observed, or t alpha is less than t observed. Greater than means towards the right. If t alpha was less than this, means it is well beyond, well in the acceptance region, means my t observed is somewhere here. So that's why my t alpha is on the right of it. It is more than this. So I will accept here. I will accept the null hypothesis because it is more than the significance level. It should be at least at this level. So at least 5% or at least 95% of the region should be there in the acceptance, and 5% should be in the rejection. So this is my critical value of t alpha. So if my t alpha is greater than this, means I'll accept it. But if my t alpha is less than t observed, which is in this case, it is less than this on the left side of this. So my t observed, the area under the curve will become less than the significance level. The p value will become less than that significance level, and we will reject the null hypothesis, what we did in this case, and we rejected the null hypothesis and accepted the alternate hypothesis that they are not equal. I hope hypothesis testing is clear. We will solve more problems and then it will become clear, but not in this video. There will be more specific tests when we discuss t test, z test, etc., chi-square test. Then you will get better understanding. But I hope the framework is clear and how to approach hypothesis testing, and the terms are clear. What is critical value? What is p-value? What is t observed? What is test statistic? These should be crystal clear by now. Okay, let's proceed. So the next thing is left and right tailed or sided test. Okay, what is there? So you saw the distribution, right? So the test statistic is like this. So what will be the, where I will measure, whether I'm measuring on the left tail or the right tail, where I'm going to measure the test statistic, or both the tails, two-sided test. Okay, so that's the question. My t observed can fall any side, right? It can be positive or negative, because then this is the 0. So it can go anywhere. So in which case, which side of the tail I'm looking, and depending upon that, we'll look on the table we'll have, which will give me the values. So we should know what we are doing. And this, whether it's a one-sided test, two-sided test, left tail test, right tail test, this will come from our alternate hypothesis. And let's understand how. Okay. So first of all, let me write left slash right tailed or sided, because it is tail test, or one or two sided test, all of them sided or tailed. So I'll cover all of them together. Concept is same. So all of this depends on our alternate hypothesis. So what is my alternate hypothesis? Because we'll not know. My null hypothesis is always same, that everything is same, nothing has changed, everything is equal. My null hypothesis remains the same across tests. So what is my alternate hypothesis? That they are not same. There is some change. Okay. So let's continue our medicine 2 sample test. So what was our so MM1 and MM2 mean recovery time, and what was the t observed? Mean recovery time of medicine 1 minus mean recovery time of medicine 2 by square root of standard deviation by n1 plus standard deviation square by n2. This was my t observed. Now look at this. So the denominator here will always be positive. Will always be positive, because this is a square here. S1 square, this is positive, and n1 and n2 are sample sizes. This will be positive, and this is sum of two numbers. So this will always be positive. Okay, this will always be positive. Denominator is always positive. So the only thing, so if it is negative, right? So for example, this is 0. So my t observed here value, what values will it take? It will depend on the numerator only. So if mean recovery time mm1 is greater than mm2, then it will go on the positive side, because this one is greater. And if mm1 is less than mm2, then it will go on the negative side, right? It will go on the negative side. So if we go on the positive side here, then this is called a right tail test. And if you go on the negative side, it is called a left tail test or left sided test. Okay, so let's go one by one. So case 1. We'll see. Case 1 is mm1 is greater than mm2. This is my alternate hypothesis. So I'll state the alternate hypothesis itself. So alternate hypothesis is that mm1 is greater than mm2. So if medicine 1 recovery time is greater than, so this term will be positive. So finally my t observed will be positive. This implies my t observed will be positive. Means, where will I have to look? Where will I have to look now? The distribution of the PDF. Here, t observed will come somewhere here, as we saw here in this case. So my t observed will be somewhere here. On the right side. Similarly, the other way around, case 2. If my alternate hypothesis is that the mean recovery time of medicine 1 is less than mean recovery time of medicine 2, then what will happen? Where will my t observed be? It will be negative now. If this is less, means this is less than this. So this whole numerator will become negative. So where will my t observed go? Towards the negative side. So my t observed will be somewhere here, less than 0. So this will be a left-tailed test or a left-sided test. Okay, this will be a right-tailed. Right-tailed. This is because we have distribution as tails. Okay, and this will be a left-tailed. And now case 3 will be, say for example, my alternate hypothesis says that both are not equal. It just states that whatever is the case, they are not equal. I don't know whether it's less or more, but both are not equal. That's my claim. Okay, so what will happen here now? So I'll have some significance level here. So my t observed, so there will be some significance level, okay, alpha. So I'll just write here. So for example, this is my t alpha by 2, t alpha by 2. This is, for example, for the left side, I'll give another number. This is t1 and this is t2. Okay. So I'll divide my significance level. Say for example, if my significance level alpha is equal to 5%, and assuming for this distribution, the curve is symmetric, which t distribution is. So I'll divide this into the two sides. So I'll make it alpha by 2, that is 2.5% on both the sides. So 2.5% here and 2.5% here. So area under the curve will be 2.5% and here it will be 2.5%. I will divide my significance level if the distribution is symmetric on the two sides equally, and now I will measure my t observed. So now t observed I'll get on both the sides. Because it is not equal, I'll consider both the cases and I'll see where my t observed lies. If it is on the extreme right side, automatically it will be less than t alpha by 2, and if it is on the extreme left side, it will be automatically less than t alpha by 2 on the negative side, t1 alpha by 2, t2 alpha by 2, and then I can accept or reject. If it is more than to this, it will come here, it will come here, then I can accept it. But both the sides, I will get. If I'm getting only one value, depending upon what values I'm getting, if I'm getting only one value, then I can check whichever side it is. If it is less or more, if it is going on the extreme left or extreme right, either of the side it is extreme, then I can reject it. Or if I'm getting here, then I can accept it. I hope this is clear. This is your two-tailed or two-sided. Okay, this will be your two-tailed or two-sided when there is inequality. Inequality means just not equal to. This is also inequality. When you have less than or greater than, then that will be more, that will be single-tailed, one-tailed, one-sided, left or right. But if there is not equal to, then this will be a two-tailed or two-sided where it can go on both the sides, and if the test is symmetrical, I'll divide the significance level into half on both the sides and I'll measure where my t observed lies. For example, if my t observed is here, either here or here, then I'll reject it because the area under the curve, this p value will be the area under the curve under this, and this will be less than my significance level, and then I'll reject my null hypothesis and accept the alternate hypothesis. I hope this is also clear. Okay, so we have discussed critical value also and all these related terms. This is clear. Okay, let's see what all things we have discussed. So we have discussed hypothesis, framework we have done, left, right, critical value we have discussed, p value also we know. Now let's discuss power of a test. Very simple. I'll discuss about this later also. This concept will come again and again. Okay, so now let's discuss about power of a test. Okay, let me move to a new page. What is power of a test? Before that, we'll just plot the confusion matrix. Confusion matrix is a performance measurement parameter, so that once the model is ready, right, or whatever we have, then we create this confusion matrix to find out how the model is behaving or performing on the test data. So I'll create another video. In that I'll discuss confusion metrics and other performance metrics in detail, but this is just a trailer of that. So we'll create a confusion matrix. Confusion matrix. Okay, so let's create a confusion matrix. So we'll create a confusion matrix for alternate hypothesis. Mhm. 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 So this is my alternate hypothesis. So this is true, this is false, this is true, this is false, this is false. So let's say this is your actual or actual ground truth or true. This is the truth, and this is your observed. Okay, this is your observed. This is actual ground truth, and this is your observed. On the horizontal, these are my actual values, which is the ground truth, and these are my observed values. So if my alternate hypothesis is true, okay, and I okay, so let's see the true and true. This is okay. If my alternate hypothesis is true and I find that this is true, then good. If my alternate hypothesis is false and I found that after that this is false, this is also good. So these are good brackets to be in. So all these diagonal elements will be good. I can have multiple entries also. Sorry. So this is good. Let me make this tick a bit smaller. Okay. So this is good. The problem is, if alternate hypothesis is false and I predict it as true, my observation is true based on the data that I have. This is a problem. So this entry and this entry is a problem. So my actual is false, but my test says that my observation is true. So we tell this as, what do we say? We call this as false positive. Okay, false positive. And if in actual this is true, but my test says that this is false, then this will be a, actually it is true, but I am telling it's a false. Then this will be a false negative. Both are false. So these are true is true. This is true positive, true negative. Okay, so we say this is true positive, this is true negative. Both are true, no problem. But this is a false positive. It is actually false, but I am telling my test is saying that this is true. This is a false positive. And actually it is true, but my test says that this is false. So this is a false negative. I hope these terms are clear. So anything which false here, this is not good. So this is not acceptable. This is not good. So I'll put a cross. So all these diagonal elements are good and the non-diagonal elements are not good. And this is what is called, so these have got other names. So this is also called false positives. As I mentioned earlier, this is also called type 1 error. Type 1 error. And this is equal to your alpha also. That is your significance level. And this is your type 2 error. This is false negatives, type 2 error. And this is equal to beta. Okay. So if this is alpha and the whole sum is 1, so what will be this value? This will be your 1 minus alpha. And this will be 1 minus beta. All this sums up to 1 because there will be total truths will be there, total false will be there. Okay. So this is your type 1 error is alpha, this is your significance level, and this is your type 2 error. And all the diagonal elements are true. Now let's focus on these entries. Okay. Quickly. So type 1 error is your alpha, type 2 is beta. So this is your. So what is the power of test? Power of test is this entry. That if it is true and I'm predicting is that if alternate hypothesis is true and I'm predicting it as true, then this is your this is a right thing to do. This is your power of test. That if it is true, I'm predicting it as true, then this is good. This is your power of test, simply put. This is your power of test is equal to 1 minus beta. Okay. That probability of, this is the probability of correctly accepting the alternate hypothesis. In words, it is probability of correctly accepting your alternate hypothesis or probability of correctly rejecting the null hypothesis. Okay. And significance level or your alpha is your false positive rate or type 1 error. Okay. So this is the maximum risk that we are willing to take to incorrectly reject a true null hypothesis. So these are just wordplay, but if you understand this, okay, so the statements will start making sense. So this is null alternate hypothesis was true and my test also found it true, and this is the power of test. This is the more important thing to understand. And the false positive rate is my significance level. This is your alpha. Okay, ideally this should be complete 100 and this should be 0, but that's not the case. Okay, alpha is generally 5%, and for medical tests we also go till 0.1%. For example, if I have a test for cancer, then it should not falsely tell that a person has cancer. Or if, for example, it's the other way around, if a person has cancer and my test falsely says that no, the person doesn't have cancer. So these kind of things, they should be very, very strict. So there the alpha is 0.1%. Okay, now let's move to the next topic, effect size. So what is effect size? This p-value or this hypothesis testing, whatever we have done, okay, it just measures whether whatever you have tested, whether it's statistically significant or not, the p-value that we have in the hypothesis testing. So depending upon that, whether it's more than critical value or less than critical value, depending upon that, it just tells us whether it is whatever we have done, whether medicine 1 or medicine 2, whatever the recovery time is, whether it is statistically significant or not. It just tells me that. Okay, it is less or more, or both are equal or not equal, it just tells me that, but it doesn't tell me the magnitude of that difference. Okay, and that's where effect size comes into picture. So the p-value only tells that whether it is statistically the test whatever you have done is statistically significant or not. But effect size measures that how much of effect is there. Because of medicine 1, if the recovery time is very less than medicine 2, so it captures that magnitude of the effect or the difference. So this effect size captures the effect. Okay, how much of effect is there? How much of effect is there? It just tells that there is some difference, whether it's significant or not. It just measures that p-value, but this tells that whether it is how much, what's the magnitude. So it captures the magnitude. Okay, also it gives us a standardized magnitude. Okay, it standardizes the value so that we can compare the values, as in correlation, right? We can compare the correlation based on the correlation coefficient. We can compare the data from across tests, across different tests and across different sample sizes. They will coming. So for example, if I'm comparing the height and age, whether height has impact on age or not, or mean height of two groups. Okay, and I'm comparing mean salary of two companies. So they are across different samples and different sample sizes and across different metrics units. One is in centimeters, one is in rupees or dollars, whatever is there. But I can compare, since this effect size is standardized and the magnitude is captured there, I can compare two effects. What was the effect across tests or across sample sizes? I hope that makes sense. Okay, so the larger the impact, okay, means more the effect size. For example, there is a formula for this that is called Cohen's D formula to measure it. Okay, and this is equal to, okay, it is for comparing, for example, it is for comparing mean of two groups. In this only, mean of two groups, mean of two recovery times of two medicines, mean of two groups. So what is the formula? X1 bar or mm1 minus x2 bar mm2 mean recovery time from the sample mean of the two groups divided by pooled standard deviation. So this is what makes it, this is the standard deviation. So let me write it. This is your pooled standard deviation. Pooled means which is pool of both the standard deviation, pooled standard deviation. And these are sample means. And the pooled standard deviation formula is, so it has also got a formula. This pooled standard deviation is equal to square root of n1 minus 1 s1 square plus n2 minus 1 s2 square by n1 plus n2 minus 2. So this is going from, I think, from degrees of freedom, n1 minus 1, n2 minus 2, or the standardization, or that Bessel's correction. Okay, we can check that. So this is your pooled standard deviation formula. So we plug this in here. So for this medicine also, we'll have the sample size for the mean recovery of mean recovery time of two medicines. We have the mean from the data that we have. We can calculate the sample mean of the two medicines. We can calculate the pooled standard deviation also, and this pooled standard deviation makes it standardized because both the units will be same. This is square root of variance. Standard deviation is the same unit as the thing that we are measuring, right? If this is in centimeter, this will be in centimeter. This is in rupees, and this will be in rupees. Okay, and this is your unitless. And this is your pooled standard deviation formula. You have all the values. You know the sample size, you know the sample standard deviation, everything. You plug it in here, and you will get a value for that. Okay, and generally this value varies from 0 to 1. And let me show you graphically. For example, if there are two samples, okay, two samples, and let me draw it. So there are two samples. One sample is like this, and another sample is like this. So this is your mean, this is your mean. So the distance between these two, if this is small, okay, this is small here. So this is your small effect size. Small effect size. If the mean is not too far, then whatever is the impacted, both are almost same. This x1 and x2 are both almost same, means the effect is small. The difference is small, means effect is small. So there can be one way it can be like this. The other way can be, it can be like this is small. Similarly, there can be some difference. This is red one, and this is, there can be some, it can be somewhat far. So if you see now, okay, now this is your effect size. This, the difference, the distance between the means here. This is your effect size. This is what is measuring, because that is what is being captured here in the numerator. Okay, so this is your medium effect, more than small, medium effect size. And either this can be like very far. I can have the red sample like this and the blue sample like this, no overlap. Okay, quite far. And this we can say that this is your large effect size. This is your large effect size. The means are going farther and farther. And if we see in terms of Cohen's-d formula, so this can be, say for example, this is like just 0.2 small effect size. Okay, d is equal to, here the d can be equal to 0.5, and here it is like, say for example, d is equal to 0.9. Okay, so depending upon the Cohen's-d value, we can compare the two effects and the effect size. The distance between the closer they are, the less is the effect size. Okay, because of this. And if they are in between and the farther they are, the larger is the effect size. Okay, I hope that is clear. For example, I'll give you just quick example that if I do a study on patients which measures the effect on the same medicine line, okay, effect of a medicine and a placebo. Placebo is like, you just give that, it's not a real medicine. You just tell person that this is a medicine, but it's not a medicine. That's what is a placebo. So you give one control group, you give a placebo, other control group, you give a real medicine, and you compare the improvement. And then you find out that the p-value is significant, that you accept the null hypothesis that p-value is 0.05. It is greater than, okay. Sorry, it is less than 0.05. So you reject the null hypothesis and you say that there is some difference between the two groups. Okay, the placebo and the medicine, there is some difference, they are not same. And then you try to find the magnitude of that effect. What is the effect of the medicine? Is it better than the placebo or not? Okay, if the effect of the medicine is very small, then the effect size will be small. If the small, but then we calculate from the Cohen's-d formula, small effect size. If it is 0.1, say 0.1, then we can say that the drug didn't have any, had minimal effect. It was just a random, by chance it happened. Okay, but if the effect size is large effect size, say for example that is like 0.9, then you can say that the drug produced the substantial result. Okay, whatever the result was there, it was because of the drug really being, okay, better than the placebo, and the drug produced the substantial improvement in the patients. This is the p-value just tells that whether it is significant or not, and after that we measure the impact, and that will come from your Cohen's-d formula, which will measure your effect size. I hope this is clear now. Now let's do a quick revision of all the things that we have done. This sums up all your hypothesis testing. What all things we covered? We covered what is hypothesis testing. So hypothesis is a claim or suggestion that is a possible explanation but has not been found as true or false. So that's the hypothesis. You say that is the hypothesis, and that has not been tested yet. And the testing actually tests that claim or that possible explanation of something happening in certain way. So that is the hypothesis testing. It is very important in machine learning. We do model comparisons or model validation, and then we do A/B testing. Everywhere we have hypothesis testing. Okay, in other fields also. And then we saw the what is null hypothesis means. That's the status quo, no change, no difference, no effect, nothing. Everything is same. Everything is equal. So null hypothesis is generally almost it is equal. Okay, and alternate is that there is some change. So for example, when we considered the medicine example, right, recovery time of two medicines, then we said that mean recovery time of one medicine is less than the mean recovery time of other medicine, or it is greater than the other medicine, and we saw that. Okay, so that's the second thing. So we understood what is null hypothesis, what is alternate hypothesis. We hypothesize that, and then we perform the test. Okay, and then I told you what are the types of common hypothesis testing that we do. So we have test of means, where we do one sample where we compare the sample mean with the population mean. Then we have two sample where we compare the sample means of two groups, and then we have pair testing, which we'll not discuss much, before and after on the same sample mean. Okay, then they are test of medians, where Moore's median test is most common. Then we have test of variances, where we go for chi-square test, F test. Then we have test of distribution, which is goodness of it. Are the two distributions together, are they same or not? We have chi-square goodness of it test, K test, Kolmogorov-Smirnov test, AD test, Anderson-Darling test, SW, Shapiro-Wilk test. So these are the tests that we do. Then we have test of correlation. We have chi-square test of independence, Pearson correlation. Then we discuss the framework for hypothesis testing. So we have 6-step formula. Okay, state the null and alternate hypothesis, then select a relevant statistical test, derive the distribution of the test statistic under null hypothesis, assuming that that is true. Then state the significance level that you want, generally that's 5%, and then we compute the p-value and see whether it is greater than or less than the critical value. And then we accept or reject the null hypothesis based on that significance level. And then using an example, we understood this. So this was the graph that sums it up. Say for example, this is your t distribution of we took a t test, and the underlying distribution is a t distribution. The PDF is here, and we said that this is a critical value, and if a t observed is greater than t alpha in this case, then you will reject the null hypothesis, because the p-value, the area under curve after the t observation, which is t greater than or probability of observing any t which is greater than or equal to t observed. This is less than the critical value area. Critical value area is 5%. This is the rejection region. Okay, and this is the acceptance region. So if your t observed came this side, then automatically your the area under the curve will be greater than 5%, and you will accept the null hypothesis. Since here it is less than the area under the curve is less than 5%, so we'll reject the null hypothesis in this case. Then we saw and the value for which is the area is more than the significance level. This is your critical value. This is your t alpha. Okay, and then we saw left-tailed and right-tailed test. That is on the base of alternate hypothesis. If your whatever is the test statistic, for example in this mm1 minus mm2, if this is less than 0, then we'll go towards the negative tail. Okay, and if it is greater than mm2, then this numerator will become positive, because the denominator is positive itself. Then we'll do the right tail test, and if it is not equal to the third one, then we will divide. If it is symmetric curve, we'll divide this significance level into half on both sides, and we'll see which side may t observed is lying, whether it's going towards very left or very right on the curve. Then we can reject the null hypothesis, because the area under the curve will be less than t alpha. And then we discussed power of a test. We saw it through confusion matrix. The power of a test is that if the alternate hypothesis is true and correctly we are accepting the alternate hypothesis, that's what is my power of test. Here also we understood what is false positive. Means my alternate hypothesis is true, but I am telling that this is false. Oh, no, the alternate hypothesis is false, but I'm observing that this is true. This is a false positive. It is actually false, but I'm telling my test is saying that that is true. I'm accepting falsely the alternate hypothesis. Okay, and the opposite is false negative. That actually my alternate hypothesis is true, but my test is saying that this is false. This is your false negative. These two are wrong. Means these two values should be very less. Okay, that is the rate of this should be very less, and these are your success. Okay, this is your 1 minus alpha. So this type 1 false positives are also called your type 1 error or alpha. This is your significance level, which we define at the starting. Okay, and then 1 minus beta is your power of test. Okay, because beta is your type 2 error, which is your false negative error. Then we discussed about effect size. Effect size is that how much of effect is there. So your p-value just tells us whether the test what we have got after the hypothesis testing, whether it is statistically significant or not. But what is the magnitude of that effect? That is captured by effect size, and that comes from Cohen's-d formula. We discussed what is Cohen's-d formula, and if the two means are, this is for means, if the two means are very close by, then your value will be coming as very low, and that is a small effect size. Means there is no actual effect. So whatever we observed, that is just by chance. And then there can be medium effect size and there can be large effect size. And then we discussed with respect to a placebo and a medicine's effect on patients. Okay, the improvement observed on the patients, and if the effect size is 0.1, means that was statistic. Whatever we have done initially, the p-value was less than 0.05. So we rejected the null hypothesis and accepted the alternate hypothesis that there is some statistical significance in this, but the effect due to medicine is very small. But if the d came to be 0.9, then that means that this medicine caused the significant improvement than the placebo. I hope effect size is clear, and that's all for this video. Thanks for watching this video, and bye for now.